start the recording. As always, if you have questions at any time, you can raise your hand in the Zoom participant sidebar and we'll call on you, or you can privately send a message to myself and I'll ask for you. We encourage you to raise your hands to ask questions yourself in person in order to make this feel as conversational as we can. So we'll generally be prioritizing questions asked in person over privately messaged questions. And in the spirit of keeping this a more relaxed and personal conversation, we also request that everyone be muted unless they're speaking, and also have their video on if you are willing and able. Lastly, for those of us who are joining us for the first time today, and if this is the first time you received one of our emails, or you feel like you're for whatever reason at risk of not receiving these emails in the future, please sign up for our Chilloquium mailing list. On the link I just posted in the chat. This is just to make sure that we don't miss sending you the invitation in case you're not already in our contacts list, such as on, say, the Harvard SPS list. We send out one weekly Chilloquium email and a reminder on the day of the event. So if you want to stay up to date on what talks are coming up, fill out that quick 15-second form. All right, so with that, let's get started. Professor Jared Kaplan is a theoretical physicist with broad interest in effective field theory, particle physics, cosmology, scattering amplitudes, and the CFT conformal field theory bootstrap. He's an associate professor of physics at the Johns Hopkins University, attended Stanford for his undergraduate and Harvard for his PhD, where he was advised by Professor Nima Arkani-Hamed. His present research uses CFT to learn about quantum gravity through the ADS-CFT correspondence. He's also working on topics at the interface between physics and machine learning, and is co-founder of the machine learning startup Anthropic. Professor Kaplan, thank you so much for joining us today.
Great. Thank you so much for the invitation. This seems like a really, really interesting event. And of course, it's always dangerous to invite a professor to something and just say, hey, talk about yourself, talk about your journey through life. Because you really might get what you asked for. And so I'll talk a little bit about physics. I'll talk a little bit more about machine learning, but I think mostly I'm kind of going to talk at kind of the meta level about how I've thought about what to work on, just kind of what my interests were at different points in time and kind of how that evolved. But I mean, most of all, please just interrupt me and ask whatever questions come into your mind, either about physics, or machine learning, or just about sort of why I worked on what I worked on, how I was thinking about it, what the challenges were, what sort of I did to make things happen. I'm just very happy to sort of make this whatever is most useful and most interesting to you. So I have a few slides, but yeah, please don't feel shy about diverting me towards whatever is most valuable for you guys. So let's see. So, okay, cool. So I guess I'll first just talk about kind of how I got interested in physics and kind of how I thought about what to work on. Because I think looking back on my education and then sort of research that I've done, it's at least interesting to me to think about where did I make a mistake? Where was I really naive, et cetera. I think I was someone, I mean, what was my trajectory? Well, I went to this nerdy high school called the Illinois Math and Science Academy. I went to Stanford and I was a physics and math double major at Stanford. I was really, really interested in and very focused on physics and theoretical physics. Then I went to grad school at Harvard with Nima, although sadly I only got to stay there for 2 years, which was, I mean, I had a really great time at Harvard, if many of you were there. My advisor moved to the Institute for Advanced Study. And so I ended up kind of living on the outskirts of Princeton, New Jersey for the rest of my graduate career. And yeah, then I was a postdoc once again at Stanford and the SLAC National Accelerator Laboratory. Then I became a professor at Johns Hopkins. And sort of dabbled and increasingly worked on machine learning. So that's kind of what I did, where I was, just as background. But anyway, I was definitely someone who was always from an early age pretty focused on physics and math. I wasn't one of the people who I think it's very healthy to be a person who doesn't really know what you want to think about. But I was really sort of if anything, overly focused on physics and math. I would say, though, that my interest in physics, I think, was on the philosophical side. I remember learning in when I was 14 that, I first learned about sort of Newtonian physics and how the universe was running like clockwork. And then I learned that, well, because of quantum mechanics, random events can happen. And I remember like hearing about this and kind of rushing to the library at my high school and trying to find books about quantum mechanics. I wanted to understand, like, is the universe really deterministic? Like, where is free will? Is that possible? So I think my interests in physics were very sort of oriented around like, kind of like, what does the universe really mean? What is really fundamentally true? How should we think about it? Stuff like that. And this will end up being kind of relevant to later on. I was also pretty interested in ethics in a kind of abstract sense. I think it was just like I was an abstract thinker, and people told me that like I should be nice to other people and I should follow the golden rule and stuff. And I was like, well, like, what is the like logical conclusion of that? And so I was pretty interested in. I really liked Peter Singer's book Practical Ethics, which I just randomly encountered in a bookstore, I think when I was in high school. I like that book because it sort of has these like really striking thought experiments if you're an impressionable young person about like, I guess the most famous thought experiment is this idea that like, if you're going to a fancy party and you're wearing like a fancy suit, but like you passed by like a pond and there was a child drowning in that pond, like obviously you would like go save the child who's drowning, even though it would be a cost to yourself. You'd get all dirty and muddy and stuff like that. Like you wouldn't even really think about it, but like there are similar trades that can be had. There's certainly similar opportunities to do good in the world, most likely, but they're just invisible. There are people far away, people that we don't know who we could probably help tremendously at like a small cost to ourselves. And should we choose to do that or not? And I think I was generally very interested in kind of like this sort of intellectual framework. It's also nice because like when you're a teenager, you're kind of like, if you're like me, you're kind of like rebellious. You're kind of like, you think like adults are a bunch of hypocrites, and like reading this kind of stuff sort of reinforces this like, oh, like what are these like adults who are telling me what to do? Like, are they really good at all? It seems like according to this very pristine sort of ethical theory, like we're all kind of questionable. So anyway, I was kind of influenced by things like that. So, but that just stayed in the background. Mostly I just did physics. I was very excited about physics. I think I had like a pretty naive theory of like how my work in life would impact the world. I mean, it was something I thought about, but I just kind of thought, well, like physics and science has generally been really good for the world. It's led to sort of tremendous progress. It's also like there's something kind of noble about it. It's very beautiful, like to like understand these deep truths about the universe, and sort of somehow this will kind of affect the world because sort of theoretical physics may be fairly abstruse, but eventually sort of the things that we learn will sort of filter down and affect technology and humanity. And to be clear, like I mentioned ethics, I mentioned impact. I really was just most excited about like understanding the universe. That was really the thing that motivated me the most. So I think impact and ethics were actually kind of a second thought, but I sort of mentioned them because they'll sort of be relevant later. I was another thing that I didn't think about too much, but I think in retrospect, I wish I had thought about more, was sort of to what extent is the world going to change during my lifetime? This is something, I mean, you can find a lot of writing and pondering about this. I think if we think about like the early 20th century, there were just tremendous changes. You could have someone who like in one generation went from a world where there was really very little technology to a world where there were like people landing on the moon, airplanes, cars, just like washing machines, sort of freeing people up from drudgery. So I think like there was certainly this period from kind of like the end of the 19th century to the mid 20th century, just tremendous progress. And that was always interesting to me because I sort of was, I think as a child, I was kind of two minds. I kind of felt like, well, like I really hope the world changes in a lot of great ways during my lifetime. But on the other hand, I wasn't really sure if it would. Like, was it going to be the case that I was going to be able to like live in a Mars colony when I was an adult? Like I sort of wondered about stuff like that as a kid. And I think this is a big question for sort of like what to do with your life, because if the world isn't going to change a lot versus if it's going to change tremendously, that might change what's sort of important to work on. I was a little bit interested in artificial intelligence throughout my life. I don't know, I like read science fiction and stuff. So I was pretty interested in it, and I was interested in it in a kind of philosophical way, but I never really did much computer science, honestly, for like the really basic reason that like when you do physics or math, like you just kind of read things, you can kind of understand everything. It's all sort of at your fingertips. And like I really hated like when I would like write a computer program and it wouldn't work, and then I have to debug it. Like I just didn't like doing that. So I didn't do a lot of computer science as like a student. I guess another sort of question that sort of another thing that I think was relevant in my thinking, and that like maybe is relevant for some of you, especially if you're kind of like more of the theoretical mindset. I feel like there's this tension between kind of abstraction and like examples and concrete things and empiricism. So like when I was an undergraduate, I remember being, I double majored in math and physics, and I was really excited about kind of like the power of abstraction. And so I was really, really excited about string theory. I remember being interested in things like set theory and category theory, which were kind of like these like fundamental theories of math. There's a lot of stuff like that that I was excited about. But like, I think an interesting thing, if you've talked to a lot of professors, is that I think actually like most mathematicians and theoretical physicists aren't quite as excited about abstraction as all that. I think like one thing that you learn when you try to do research and kind of like really understand things is that actually in a lot of ways, like the way that we understand things is through sort of examples and concreteness. And I think that like there was a sense in which I sort of intellectually did this 180 where as an undergrad at first, I was very excited about kind of like the most like kind of fancy string theory and math. And then I kind of did a 180 where I learned about these other ideas like effective field theory and inflation. So I can explain briefly what that means. So a very basic question you can ask about physics is, why is it possible that you can understand, say, like how a baseball flies or like how to cook eggs without knowing nuclear physics or string theory? You might have thought that the like fundamentals of physics would be very relevant to how even macroscopic objects behave. And if you didn't understand the fundamentals, you couldn't really make any kind of prediction or theory. And sort of obviously that's wrong. Obviously, like you don't need to know quantum field theory or string theory to like plot the trajectory of a baseball. But like there's some question there of like, why is it that fundamental physics isn't like goes away and disappears? And effective field theory is sort of a fancy modern physics way of trying to explain how this happens. How when you look at big phenomena like long macroscopic phenomena at long distances or sort of low energies, the details, the microscopic details go away. Kind of in the same way that when you look at a computer screen, you don't see all of the pixels, you just see like a big image of something. And so there's this effective field theory idea which kind of explains quantitatively why microscopic physics becomes invisible at the macro scale. And there's sort of a similar thing that happened cosmologically. You might think that to understand the way that our universe is today, you need to understand its origins, like very, very close to the Big Bang. But there's this theory of inflation that says that the universe expanded very, 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 very rapidly. And so all of the sort of microscopic physics and the sort of early, very hot universe got kind of diluted away and expanded away. And all that's really left is relatively sort of low energy phenomena. And so on the one hand, you might have hoped that by studying cosmology, you can learn very easily about fundamental physics, the sort of smallest stuff, the highest energy stuff. But in fact, it's actually difficult. It gets kind of diluted away. So there's a sense in which inflation in time is a little bit like kind of effective field theory. Yeah, go ahead.
I have a brief question, yeah, if I may interrupt. Yeah. Because I'm a little ignorant of effective field theory, but this kind of reminds me, this notion of taking a sort of a microscopic system and then kind of looking at it in a macroscopic lens, and then the microscopic details kind of washing away, is to me reminiscent of the approach that, the statistical that is taken in statistical mechanics. Is there some sort of like either connection or like difference between the approaches that, say, effective field theorists might take from, say, like a someone who works in statistical mechanics? Or maybe there are similar approaches, or maybe they're completely different.
No. That's a great and very deep, insightful question. So actually, statistical mechanics and quantum field theory and quantum mechanics are kind of like deeply the same thing. So you're exactly right. So this is the kind of thing you study in statistical mechanics, where sort of like small fluctuations sort of like become invisible at the macro scale, and there's only a few important sort of macroscopic variables, like famously like pressure and temperature and volume, things like that. So these are actually very, very closely connected. And there's a direct way in which they're connected. For example, so in quantum mechanics, there's a sense in which you're kind of like averaging over a lot of different like random things that could be happening in the wave function. And in statistical mechanics, you're sort of averaging over a lot of random things that can happen because you have a lot of degrees of freedom that are all fluctuating. And the mathematical description of those two things is in fact actually very deeply connected. It's sort of identical. So there's this thing that there's sort of the path integral that's often associated with Feynman. And it's literally, I mean, if you haven't heard this, it kind of sounds wild. If you take time to imaginary time in the quantum mechanical path integral, you actually get a description of the partition function of a statistical physics system. So these things are closely connected, and it's literally the same math that describes both of them. It's a great question. Any other questions?
Yeah, could you expand on that imaginary time path integral to the partition function? That's really interesting.
Yeah. So, so what happens is that in the, I mean, I can sort of kind of sketchily point at it. So, I mean, in quantum mechanics, if you've studied quantum mechanics, there's this wave function, and the wave function, like in time, is literally waving in the sense that like time evolution is some basically sine or cosine type function, or e to the I energy times time. So basically, like time evolution is sort of these oscillations with various frequencies, and you superpose those oscillations to get kind of like the semi-classical behavior. So there's sort of the sense in which like e to the I energy times time, I guess divided by h bar, is the way in which wave functions evolve in time. Wave functions with definite energy. And partition functions have Boltzmann factors, which are e to the minus beta temperature, e to the minus beta energy, right? So you get like e to the minus energy over temperature. And so literally, if you take this thing that's fluctuating, I mean, sines and cosines, and you analytically continue them, you send time to I times time, then you get hyperbolic sinh and tanh, which decompose into exponentials. And so that's literally sort of like the simplest mathematical way in which these things end up being connected, is that like sinusoids analytically continue into hyperbolic things that then end up being the Boltzmann factors in a partition function. Cool. Well, anyway, I mean, there's only so much I can say, but that's something that's sort of like some pointers, but you could definitely look this up, and there's I mean, you could spend a year like learning all about like all of these kinds of connections, but yeah, it's really cool stuff. So anyway, I think this general idea that the microscopic fundamental physics was really, really hard to probe, and that only kind of universal features would be visible to us as kind of long distance observers. Long distance because the scale at which we can do experiments is vastly bigger than, say, like the fundamental scale of things like quantum gravity or grand unification. So anyway, all of these things made me think like, oh, wow, I should really focus more on experiments and phenomenology. So that meant sort of like Large Hadron Collider physics. Like it seemed perfect when I was going to grad school. The Large Hadron Collider was just starting up, dark matter, etc. And so I did work on kind of cosmology and LHC physics and dark matter for many years. Who's our question? Yeah, so I worked on that kind of stuff for many years, but then sort of like towards the end of my PhD and as a postdoc, I kind of like got back into kind of like studying things like quantum gravity. And I think that like the motivation there was really that I wanted to I wanted to work on things that were kind of conceptually revolutionary. Like, I think if you kind of study the history of physics, like you should very much envy the physicists who are working in like the 1910s and 20s, sort of discovering quantum mechanics. I mean, like people make a big fuss about special and general relativity, and it's like kind of a big deal. It's pretty exciting, but there's a sense in which quantum mechanics is just kind of like the most revolutionary thing that ever happened, in the sense that it just tells you that like what the world appears to be. Like the world appears to have objects, and they have locations in space, and they have like velocities. And like that's pretty intuitive to sort of any person. And quantum mechanics really just says, no, that's just not what like the fundamental language of reality is. It's really that there's this vector space called a Hilbert space, and states are just these abstract vectors in this vector space. It's really, really crazy. And so I think that like, I mean, all physicists, I think, probably should be jealous of the people who got to kind of discover quantum mechanics. And so I kind of felt like, well, like all of this like dark matter stuff and LHC physics stuff, I don't know, like it's interesting, but like maybe we're not going to discover that much. And it doesn't like is adding one more particle to the list of like tens of particles that we know, or I mean hundreds, depending on how you count. Like, is it really that exciting? So I kind of got more interested in quantum gravity again, because there's this idea at the heart of the subject that is very revolutionary. This idea of the holographic principle, that the sort of true theory of the universe should really have something like fewer space-time dimensions. And that like the fact that we feel like we live in 3+1 dimensions is in a certain sense maybe an illusion. And really the fundamental theory is lower dimensional. It just sort of seems really, really like a big update in kind of how we think about the world. And so I was kind of excited about that. And I thought, well, if it's like this really big change, there must be a lot of sort of very basic things to understand about it. And so I spent maybe the largest part of my physics career thinking about quantum gravity from the point of view of this thing called ADS-CFT. So, I mean, anyway, this is this problem of how to unite quantum mechanics with general relativity. It's extraordinarily unlikely that this will be of any kind of practical relevance to us as like people sort of building technology in the universe. But it really just suggests that sort of fundamentally, the way the universe works is very, very, very different from what we would intuitively expect. And therefore there's sort of a lot to swallow and a lot to explain. I mean, I'm not sort of gonna talk a lot about this. There are like, I mean, in this day and age, like, I mean, I have a bunch of like YouTube lectures on kind of like why holography is true. I even have this like cartoon that I worked with an animator to make about it, that I sort of linked here. So I'm happy to answer questions, but I probably won't go into it in too much detail. But this weird abbreviation ADS-CFT is this sort of technical way in which this holographic principle is really kind of like implemented. It's sort of a mathematically precise theoretical universe where you have quantum gravity on the one hand and a lower dimensional theory called a conformal field theory on the other hand, and they literally are two sides of the same coin. They're really describing the same thing. It's called a duality because there's sort of really two pictures of the same thing. And so you can sort of actually understand how it is possible that, like, say, we could move around in a three-dimensional world, but somehow a two-dimensional theory would actually describe that physics. So that's something that I worked on a lot.
Just a quick question.
Yeah.
Do you think you got most interested in ADS-CFT because of the richness of 2D CFT, and then like relating that to the like holography theory, or did you get more interested in like the holographic theory because of the richness and like unboundness of 2D CFT?
That's a good question. So I think like to me, I mean, just as background, two-dimensional conformal field theories have a much, much larger group of symmetries compared to higher dimensional conformal field theories. And that's this sort of richness. They have this Virasoro algebra of symmetries. And the Virasoro algebra actually kind of is the thing that governs, in some respects, the gravitational force. In three-dimensional quantum gravity, this sort of two-dimensional Virasoro symmetry kind of controls gravity. So I actually would say that like it was sort of the other direction. I mean, when you're doing research is really, really hard. And you spend a lot of time being confused and not knowing how to make any progress. And so I did a lot of work on two-dimensional conformal field theory and its relationship to 3D gravity, because I wanted some sort of playground where it was possible to make kind of like really precise, exact statements about how quantum gravity would work that kind of go beyond the description that's available from general relativity and what we call perturbation theory. So for me, that was the main motivation. And then there is a lot of beautiful sort of mathematics and physics in two-dimensional conformal field theory. But for me, it was more like I was just trying to find a trick that I could use to sort of get the answers more efficiently, and at least try to get the answers to really hard questions. That was my motivation.
Thanks. That makes a lot of sense.
Cool. So yeah, so that's ADS-CFT. So yeah, so then so what about like, so I've also worked on artificial intelligence, and that's actually like kind of most of what I'm doing lately. So so why that? Well, I guess it was a few things. So one is that like, I think like some of the most interesting questions you can ask are sort of like, what is this universe that we live in? And kind of like, what is intelligence? What is intelligence has two sides, I guess. There's like literally instrumentally, like how do intelligent minds like do things, and like, what is that? And then there's also this sort of more philosophical question of kind of like, what is consciousness? What are kind of qualitative experiences? What are qualia? But anyway, I think they're both pretty interesting questions. I think when I was always very focused on physics when I was in school, but like also I sort of just didn't know whether AI was going to be exciting. So I guess like I didn't really understand like what will progress in AI look like, where is it headed? Like would AI research make a ton of progress soon, or would it take like centuries? Is it just sort of like a total unknown? And I guess to me, until maybe 5 or 6 years ago, like I think I just viewed this as pretty unclear. And I guess like the dichotomy I had in mind was something like, is artificial intelligence kind of like this thing that requires some lone genius, like say Andrew Wiles proven Fermat's last theorem, or is it kind of like more like an engineering task, like building a bigger steam engine or a better internal combustion engine, whatever. In other words, are there just sort of like a few pretty easy to understand principles associated with intelligence, and then basically just throwing more data and computation at some simple algorithms would actually get you at sufficient scale to sort of intelligence? And of course, I guess the second isn't totally crazy if you think about evolution. Like our brains evolved. Evolution is really dumb. Like evolution was just like a very big experiment with a lot of pieces, but without any kind of like brilliant genius sort of orchestrating things. At least that's how I think about the universe. So that might suggest this sort of latter picture. And I think in the last decade, which was all sort of after I finished my PhD, I finished my PhD in 2009, but sort of since 2012 especially, there's been tremendous progress in AI research. And as I'll briefly tell you, I mean, my interpretation of these results and work that I've done myself leads me to believe very strongly that it's sort of the second picture, that like AI is really something where you don't have to be a genius to understand it. It's actually way simpler than physics. And probably it's the case that if you sort of train machine learning models with increasing amounts of data and increasingly many fast processors, you can just sort of steadily see gains in the same way that if you like build a bigger steam engine, you'll get a more powerful steam engine. And so like these are some like plots from a paper I wrote a couple of years ago that I think are like kind of most striking in this regard. Basically, what these plots are all showing is kind of the same. They're showing that test loss is sort of like the potential. The loss in a machine learning model is basically sort of like measuring how well it understands the data. Oh, sorry.
I think we have a question in the chat.
Oh, great.
If you want to go ahead and ask.
Yeah, sorry, just a quick question. How did you come to consider working on machine learning, given your distaste for coding and technical?
Yeah, no, that's a great question. So I guess I was going to sort of get to that on the next slide. So maybe I could just say that now. So a lot of it's like about like who you're friends with, I would say. I have various friends from undergrad, grad school, et cetera, like who were working on AI, even though I wasn't working on AI. And some of my friends in particular were like particularly both like excited and concerned in the sense that they were sort of telling me that like they really expected AI progress to be very rapid. They basically had some proto view similar to what I was talking about in the last a second ago, that like it was kind of just going to be like dependent on faster processors and more data. And I think that like a lot of my friends were, so I have a lot of friends who are sort of interested in this, I guess you can call it a movement called effective altruism, which is part of the reason why I mentioned this sort of stuff about ethics and Peter Singer in the very beginning. They're very interested in sort of these questions of like, how can you think kind of scientifically about how to have the biggest impact for the better, for the good in the world? And in particular, that means like, how can you identify possible risks that like could make things very, very bad in the future and sort of mitigate them? And so a lot of my friends are sort of more or less kind of like embracing this kind of worldview or this kind of approach to thinking about things. And so a lot of those friends were interested in both sort of doing good and AI. And they were telling me like, you should really start learning about this stuff. It seems like it's really important. It's going to like have a big impact. I was super skeptical of this at first, as I think like anyone should be. I mean, basically, anytime someone tells you that the future is going to be very different from the past, you should be skeptical. I mean, like just guessing that the future will be a continuation of the past is usually a really good bet. You can like usually beat pundits at like predicting the future by just guessing that that's what's going to happen. So I was very skeptical of this for a long time. But nevertheless, I was sort of like interested in it, and I had a lot of discussions with friends about it. And I sort of was like increasingly interested. I think AI research was making a lot of progress, and so it was just intellectually interesting, and there was sort of this extra motivation. And so I think something around maybe 2017, I just sort of was like talking to a lot of my physics friends, and we kind of formed kind of like a journal club reading group to sort of read a lot of AI papers and discuss them and start kind of playing around to learn more about the field. And as I said, I think it's pretty easy. Like what you need to know to do AI research is much less than what you need to do like physics research. There's a sense in which like most things that sort of have had an impact on AI happened in the last 10 years. And so how much could there be to know? There just isn't that much. And so yeah, I kind of got increasingly convinced that maybe there was something to this idea that like we were going to build AI models that in the not too distant future were capable of doing a lot of the things people could do. Therefore, that would like be a big change. It would be kind of like an industrial revolution again. And those were some of my motivations. Like at a nuts and bolts level, the way that I got involved was like, we had this reading group. So a bunch of my physicist friends and I were like learning about AI for maybe 6 months or a year. And then I was on sabbatical, and one of my friends was kind of like a team leader at OpenAI, which was one of the kind of major AI research labs. And so since I was on sabbatical, I said, oh, like, hey, like, how about for this summer, I'll just like hang out and collaborate with you guys. And like, you don't have to pay me. I'll just sort of like hang out and work on this stuff. And my friend was like, yeah, sure. Like, I think we can do that. We can make that happen. And one of my friends from physics, who was a physics postdoc in theoretical physics, was leaving physics to go work in AI. And so he actually joined OpenAI as kind of like an employee. And so he and I kind of collaborated on some of the stuff that like the plots that you saw in the last slide. So that was sort of how I got interested. So it's like very important to have friends all over the place who are doing interesting things so that you can like ask them to let you kind of like volunteer on their research efforts. So yeah, anyway, these are just some plots that we made that are sort of showing basically how well language models can sort of write in a certain sense, as a function of how much computation you use to train them, how big of a data set of just text you scrape from the internet, and as a function of sort of how big your models are. And the striking features are that these results are very, very predictable. I mean, these are like the kind of plots that you get when you do a physics experiment, but it's sort of a machine learning experiment. And they just sort of show very clearly that you kind of get better and better performance predictably as you scale these things up. So that was something I worked on. And I think this is the kind of thing that to me makes a pretty convincing case that these lines that span like many orders of magnitude in sort of like resource inputs are probably going to continue. People can build even bigger models than say GPT-3, if you've heard of GPT-3, and this kind of stuff is going to continue. So that was sort of
I
how
have
I
a
got
quick question about that.
Yeah,
oh,
sure.
Sorry.
Yeah, go ahead.
Okay, I'll go first. So it looks like you have a lot of parameters, and I'm wondering how would you interpret that into math or physics?
Yeah, so it's very much, I think this is very much like statistical physics, where like if you want to understand how like a semiconductor works or something, it's pretty hard to understand from first principles by like describing all of the individual atoms. But of course we have statistical mechanics and other fancier modern theories that sort of describe that give you some effective description of the kind of like macroscopic degrees of freedom in materials, in atomic physics, et cetera. And so I think in machine learning, we're already in a regime where there are billions, or probably soon there will be trillions of parameters. I mean, these models keep getting bigger and bigger. I think there have already been machine learning models with 1 trillion parameters. So you're really in this like law of large numbers regime, like you are in statistical physics, where each parameter. So what is a parameter? If you're not familiar with AI lingo, like all AI is like curve fitting. All it is like you've been in a situation in some physics lab where you got a bunch of data points and you made a scatter plot and you try to draw a line that goes through all of the data points. And all machine learning models is really fancy big versions of doing that with kind of real world data. That's when you get down to it, that's all they're doing. It's not anything really more complicated than that. And so if you're fitting like a 3rd degree polynomial to some data points, then you have like 4 parameters. And these parameters in these machine learning models are the same thing. They're just, you have billions of parameters or trillions of parameters instead. And they're very much analogous to, you should think of them as being kind of like atoms in a material, where like the atoms in the material are interested in sort of like the energy as a function of the positions of the atoms. In machine learning, there's sort of this loss, which is basically how well are you fitting the data as a function of how you configure the parameters and how many parameters you have.
So my question is actually very similar to that. I guess I've heard some excitement around literally using the methods of statistical physics to analyze what happens in this really big model regime. And I'm curious what you think of that.
Yeah, I mean, I think it's always like when you do interdisciplinary work, I like tend to sort of be biased against like literally trying to keep doing the thing that you're doing in one field in another field. I think like usually the way that like transfer of information works is more like meta. It's more like the methodology you use. But I do think there are literal translations. I mean, maybe the one that's most direct is that there's something that theorists call the large N expansion. It's sort of like often viewed as kind of a quantum field theory thing, although there are versions of it in math. Basically, the large N expansion is sort of like, if you have some model that depends on some matrices, then you might take the limit that the matrices, which are n by n, get to be really big matrices, and try to do some kind of expansion in the limit that the matrices get really big. And these machine learning models are actually built out of matrices. They're really just a bunch of matrix multiplications strung together. And when the models are big, that means the matrices are getting big. So like in GPT-3, there are matrices that are like 10,000 by 40,000 matrices. So they're really big matrices. And so this sort of large N expansion that like to theoretical physicists was sort of invented by 't Hooft to describe like the strong force does directly kind of apply. And it goes under, in the machine learning literature, there's something called the neural tangent kernel, which sounds, anyway, there's some there's some buzzwords there, but like this neural tangent kernel is really what you get when you take the large matrix expansion of neural networks. And it's really very similar to sort of the large N expansion. In fact, friends of mine have shown you can like do a Feynman diagram expansion in order to like calculate effects in machine learning. So there are really a lot of parallels like that. And I do think it's reasonable. It's like in physics, you can never really solve things exactly. you can never really solve the thing you care about exactly. You can only solve things like orbits and harmonic oscillators, and then everything else is an approximation. So I think this large N expansion is a very nice natural approximation in machine learning, and it is very close to physics.
Cool, thanks.
Cool. Yeah, so I don't know if this talk has any like takeaways. I think I wrote some, since I'm old now and I can claim to be wise and dispense wisdom. I think some takeaways are sort of like, think carefully about like what you actually think is going to happen in the world and what you think is going to be important and sort of what's interesting and important to you. And I mean, people are always telling you this, but like, do things that you really care about and are excited about. Try to figure out a way to be able to do things that you're really, really interested in and excited about. A slightly less obvious piece of advice is from someone who like, I guess like I've worked on different areas of I don't know, like science, but like another piece of advice is sort of go really far in one direction before you change directions. I think like if you're interested in many different subjects, I think it's like really good to like choose something and like really go in depth in that thing and get like really, really far and like become an expert. And then maybe think about it and decide and do something else. But I think it's like, I think this algorithm is much better than sort of like any kind of paralysis where you're kind of like, I don't know what I should do. Like, should I work on A or B or C? Like, honestly, like life is pretty long and it doesn't matter that much, like what you work on at any given point. I think it's like very valuable, like once you've sort of really gotten involved in something, to work on it for like a couple of years at least, so that you can really become an expert and have kind of like deep insights. Because it just sort of takes a while to like sort of like load enough information into your brain so that you can start like actually having ideas that other people haven't had before. And I think it's sort of worth doing that. So yeah, like I've known really successful people who spent like a year or two working, or more, like 3 or 4 years, like working on things that like they then stopped working on, but I think it was still valuable. Like for example, the friend who kind of got me into AI research, Dario Amadei. I mean, he was sort of the leader of research at OpenAI. He's the CEO of this new company we founded, Anthropic. I mean, he first started out doing cosmology, and then he like did a PhD thesis on like neuroscience. And he like spent a few years working in like bioinformatics. And then he started working on machine learning and AI and got involved in that. But I mean, I think like he changed what he was working on many times, but he spent like a few years really like delving into something before changing direction. And I think that's good. Yeah, I don't know. Changing directions though isn't as hard as it seems. I mean, don't sort of feel like don't be so scared that you don't do it if you want to. Just like ask people for help. I think people are usually like, if you're really just interested in something and you don't really have any ulterior motives, but like that you're interested and you like want to learn about stuff, like most people are like really just like pretty happy to help you. Most like people who do research are just really excited to like have someone like talk to them who like really is just interested in them and what they're doing. So like ask for help and like keep in touch with your friends who do different things. And I think it's not as hard as it seems. And then I guess the final thing is like, I was in academia for a very long time and I really loved it. I really like academia. I think it's great. Like I also have like now worked at like kind of like quote unquote industry research labs, like
Sorry, Professor. Sorry.
Oh yeah, go ahead.
I think there was a question from Tianyi. Yeah. I missed it, but Tianyi, you can go ahead and ask your question. Oh, sorry. I don't think we can hear you.
Can you hear me?
Yeah, now we can.
Okay. So back when we were talking about kind of the essence of machine learning being essentially like curve fitting, essentially it's like a equation with many parameters. It kind of reminds me of a talk I had with my quantum mechanics professor in the spring, that essentially one of the biggest difficulties in quantum mechanics, and which is why it's like less useful in realistic cases, is that you often need to solve the Hamiltonian, which is become like a matrix with millions of dimensions, and that could cost months for even like computer clusters to calculate. And I wonder if that, because that sounds like a similar scenario in machine learning, that we are trying to solve these equations kind of more efficiently, but with like a bearable loss of factors. It's like not exactly solving the simulations, but instead like with the, say in deep learning or similar fields, like we hope that the machine can sort it out like a simpler algorithm to kind of reduce massively the parameters we actually need to calculate. And I wonder if like there are like two things in this context that are kind of different to me, and I wonder which one is machine learning more or less involved with. So the first is that in every specific context, we are trying to simplify the question, which is, say, the Hamiltonian was like a million dimensional matrix, and we want to simplify it to, say, 10,000 without getting much loss in the result? Or are we trying to figure out an algorithm so that we still do in a million dimension matrix, but we do it more efficiently? So it's more or less about like either we simplify the question or do we try to find out like a cheap way to solve it?
Yeah, so I think both of those approaches are things that people try to do in machine learning research. So I think the scenario that I think is maybe the most, the case where like maybe a physics problem like what you're describing in machine learning are most similar is if you use the variational principle to try to like find the ground state and the like low energy states of a Hamiltonian. There you're doing something that's sort of like almost exactly the same thing as like trying to minimize the loss in a machine learning model. So I think that's the case where it's closest. I think in physics, we often have very complex, clever techniques for sort of solving physics problems. And it's often the case that we sort of have a fixed physics problem and we want to solve it. And so we find increasingly clever techniques to do that. In machine learning, it's sort of unclear where the sort of frontier to the trade-off is, because if you have a small machine learning model, you might be able to use clever techniques to find like a better value for the parameters to describe your data. So the process of finding good parameters to fit the data is called optimization in machine learning. And you can try to find more intelligent, clever optimization algorithms, but there's sort of this other direction you can go in, which is you can just make your machine learning model more powerful and bigger and use relatively dumb optimization techniques. And I think thus far, like making the model bigger and using relatively dumb optimization techniques has been kind of the most fruitful way of getting better models. And so that's sort of the direction I think things are sort of more headed. But you're certainly right that like there are a lot of kind of clever ideas for solving these problems in physics, which in theory you might expect to apply in machine learning, but they haven't sort of been able to be leveraged to the extent that you might expect.
Okay, thanks.
Well, Professor, if I can like ask a follow-up question on that. So when you're referring to like these like dumb models, or sorry, these like dumb optimizations with broad models, are you talking about like, say, are you referring to like maybe like a very deep neural net with like a really wide net, like a really like a deep neural net, for example, with a really vast number of nodes in each like hidden layer, for example?
Yeah, so basically like 99% of like sort of neural net models, like, which is sort of all, I'm basically only talking about neural net models for the purpose of this discussion. Basically all of them are optimized using some version of just stochastic gradient descent. So what that literally means is that, I mean, the words sound fancier than the algorithm is. I mean, if you have some potential energy as a function of some parameters, which is what the loss basically is, then like a way that you can try to find the minimum is you just choose a random point in parameter space, then you compute the derivative of the potential with respect to the parameters, and you take a bunch of small steps in the direction of the derivative, and then you get to a new point, you take the derivative again, you take another small step. So that's basically very slight variations on that approach are the way that all of these models are optimized. And there are really basic things that, I mean, as a physics student, you could easily come up with where you might think that you could do better. So for example, you can use Newton's method, where you use both the first and the second derivative of the potential to try to update your parameters. But the problem is that for technical reasons, you sort of can't really, people have not really been able to convincingly score any wins in optimization by using even the second derivative. I mean, the reason is that the second derivative is the Hessian. So the Hessian is a matrix. And so if you have a billion parameters, then the Hessian is a billion by billion matrix. And to apply Newton's method naively, you need to invert a billion by billion matrix. And that's just not a tractable problem. And so that's why no one uses the Hessian, and therefore, I mean, not no one, but very few people are sort of using that. And people have tried. I mean, very smart people have sort of tried to figure out efficient approximations where they could use, say, the second derivative for optimization, but none of those techniques have really become that widely used. They're not better than kind of like very slight variations on this basic gradient descent approach. So that's sort of like basically all people do. I mean, there are slight variations that I could go into, but they're not really that interesting.
Thank you so much. And I think there's another question from, apologies for the mispronunciation, but Nora, you can go ahead and ask a question.
Okay, thanks. So my question, I guess, was more in general about like your path in physics, especially given like your interest in like philosophy and like other things. Like, did you ever feel like there was like a tension between like STEM and doing like a more like philosophical route, like outside of STEM? And do you feel like AI was sort of the place where those two interests converged more neatly than perhaps your previous research in like more theoretical physics, like with the collider? Just sort of like how to orient yourself if you have like these two different interests in like philosophy and then like science, and like, because some people I think that they're like contradictory, but I think you've like found that they're more related than not.
Yeah, I think that's a fantastic question. I think I think that like my interest in both physics and AI were like at least somewhat philosophical. But I think that it's absolutely the case that when you that if you work on AI, there are a lot more sort of both philosophical questions and also just kind of like real world practical questions, at least compared to like the kind of area of physics that I was working in, like quantum gravity. So I do think that there probably is more of a sort of synergy of like, say, like interest in the humanities and philosophy with AI than there is with something like theoretical physics. I mean, especially because as the AI models get better, like I think GPT-3 really writes like quite compelling like prose and poetry and things like that. And I mean, I think those things are going to continue to get better. And so there is sort of like this like kind of like melting pot of different disciplines that are really relevant for thinking about AI. So I think that's correct. I think one thing that's different though is, for example, like in theoretical physics, you get to do, well, it just depends on what you're interested in. In theoretical physics, you get to do a lot of like really beautiful math. And I think there are a lot of things that work in theoretical physics in a way that just like very deeply satisfying, where like you have these very complex theories that fit together sort of in perfect ways to describe pretty much all aspects of the universe, all aspects of the universe that we've been able to test. And I think that like at least my experience in AI is that like things are more primitive and there's much less of that. So I think there are sort of like things that are available in physics research that I've at least found in some ways more satisfying than in AI. But you're absolutely right that I think there's just like more contact with philosophy and the humanities and kind of the rest of the world in AI right now.
I kind of have a follow-up question to that. You kind of talked about how you kind of got into a lot of these subjects from like a very philosophical standpoint and like wanting to, understand things deeper. But how do you see the trend of interpretability in AI and like the black box models that like GPT is, because there's so many parameters? And how do you see the future of interpretability, specifically in like ethical questions where we have like results that need interpretations?
Yeah, I think that's a great question. So I think interpretability is an area that I'm pretty excited about. So I think that one way that I kind of think about the current state of at least my understanding of AI is there's sort of these ideas like this large N approximation and the sort of scaling laws that I showed a plot of, that I think of as being kind of like the macroscopic like description or the macroscopic phenomena of AI. And then I think there are these sort of, there's like research by like, for example, like Chris Olah is a friend, like on sort of like the sort of what I think of as the microscopics of AI, which are sort of like how do individual neurons work, like how do individual neurons fit together into circuits, like in order for AI models to make decisions. And I think that connecting this kind of like very microscopic picture of what are the individual neurons doing with a sort of macroscopic picture of kind of like how is overall the system behaving, how is it scaling, seems to me like an exciting frontier for kind of like further work. And I do expect that they'll fit together. In terms of the sort of ethical issues, I think interpretability is sort of like, it's very different from a lot of other techniques that we might use to try to understand AI or make it quote unquote safe. For example, one way of trying to make AI safe is to sort of try to collect a lot of really high quality human feedback on like what we really want the AI model to do, and then train it to sort of actually do what's helpful, honest, useful, factually accurate, et cetera, to people. But that's a very macroscopic approach where you like aren't opening up the black box. I think interpretability is sort of this other approach where you do try to open the black box and try to figure out how decisions are getting made. And I do think that it might be able to help in this way, or it might be able to sort of tell us something about, at least if you have a model that's like really making a specific, relatively simple decision that's high impact, interpretability might allow you to sort of try to decompose that into some of the kind of like constituent factors. But I don't think that we've had like fantastic successes at that yet either. And it could be like a really hard problem where the models are too complicated, they're too big, et cetera. So I think like sort of the jury's still out, but I think it's like a really important area for kind of further research.
I think there's a question from Billy next. Go ahead, Billy.
Yeah, actually, I have a question about like how artificial intelligence can help discover new physics, like especially the physics beyond standard model. If we simplify this idea, like, is it possible that a machine learning algorithm can invent imaginary number?
Yeah. So, I mean, I think probably it is eventually. That's my view. But I mean, I think there's sort of like two levels. I mean, there's sort of like, how can I use machine learning in physics research in the near future? I mean, many people are already using it to great effect. Like I have colleagues at Hopkins who've like using it to like greatly accelerate like data analysis in cosmology, or to be able to make like our use of telescopes much more efficient, so that telescopes only spend a little bit of time looking at each star until they find the star that's actually interesting, and then therefore maybe you can use telescope time like 10x more efficiently. So I think there's a lot of opportunities for that all over the place. And then there's sort of this like more general question of like, are AI models going to be able to be like better than humans at like doing mathematical research or theoretical physics research and things like that? And I do think that they will be better than us at that. Like I definitely expect, basically, like I'm a person who thinks that that'll probably happen in my lifetime, that they'll sort of just be like better at basically all intellectual tasks. And that's part of why I'm working on the subject, because I think that implies that there will be like really dramatic changes in society that like we sort of need to like attend to and think about hard and try to kind of like push things in a good direction. But yeah, I do think that will be possible. And then concretely for that specific question, I mean, there are a lot of people working on AI for sort of theorem proving. I have like a friend who's at OpenAI who's working on this. A lot of people at Google, like I think maybe famously like Christian Schetti is working on this. I think there's a lot of interest in kind of like automated theorem proving. Like, can AI models like learn to sort of figure out the path to putting together information they know about math to prove some new theorem? Can they kind of like discover new quote unquote interesting theorems, things like that? And I think there are some signs of life in that direction. I don't think we're at all at the place where human mathematicians are replaced, but I do think that like in kind of like on the sort of decade timescale, I would expect a lot of progress.
Hey, I don't know if
Thank
this
you so
is
much.
like appropriate for me to butt in with, but I actually work on this for my full-time job, like machine learning for theorem proving. So if any of
Oh,
you are
awesome.
curious, like feel free to message me about it.
Okay, great. Awesome. Yeah.
Wow, thank you so much.
And well, yeah, maybe this is more of a comment than a question, but I think it's interesting that you went from, you know, studying this holography, which is the notion that there are fewer than like 3+1 space-time dimensions, to the idea that, well, maybe there's more like dimensionality to this sort of physical data than we should be able to grasp, you know, using normal physics methods. So, or I guess maybe I'd ask, like, do you think that, I mean, machine learning is used in many areas where there's this really high dimensionality, and it's kind of, it would be impossible for someone to like understand this. Like it wouldn't, that's not a computer. It's much more tractable for a computer to understand. So do you think maybe like a lot of the areas of development in physics might be, I don't know, pollinated, as it were, by like examining higher dimension like data sets, or using like more dimensions to look at physical principles?
Yeah, I mean, I think quite possibly. I mean, I think that I feel in many cases these dimensions are sort of abstract. Like when we think about like physics, there's some way that like our brains are conceptualizing all of the ideas and sort of like sorting through them and putting them together. And like I think that's a lot of where these sort of like high dimensional spaces exist. But yeah, no, I think that makes sense. I'd also say like the like counter argument to like about, oh, maybe AI won't make much progress or something like that. I think like one of the key questions is sort of sample efficiency, that like people are able to learn things with like a very small amount of data. And it's kind of unclear, like, well, current machine learning models typically use on the order of maybe like 1,000 times more data than a person to like learn the same thing. That's not super precise. But I think there is sort of like a vague rule of thumb that something sort of like on the order of 1,000x. And so, I mean, there are many people who think like, oh, AI models are really dumb and they don't really know anything because like they're so much less sample efficient than people. My impression, I mean, maybe you can chime in, is that like some of the theorem proving efforts are kind of like data set size limited. So like one reason why like say GPT-3 is really good is that there's just so far kind of like a nearly infinite amount of text on the internet that you can learn from, and or even just text in books. But if you have like a fairly small data set, then you're limited by this sort of sample efficiency issue in ML. So that would be kind of like the usual argument that's given for why these models are sort of limited, is this sort of lack of sample efficiency. And of course, then there's just a question of, well, maybe you could just overcome it by brute force, and you still end up getting a model that's very intelligent. So it had to look at more data. So what? But anyway, that's sort of, I think, one of the key questions that people ask.
Hi, I have a question that's more about deep learning, but I'm just curious if you think we'll kind of ever reach a point where you can train a neural network and it'll just really stop making very silly mistakes. Kind of like how right now with convolutional neural networks, you can train them again and again. And if you do a tiny thing where you'll put like a little block in front of a stop sign, it'll read it as a 45 miles per hour sign instead, even if this neural network is like very, very efficient and surpasses human performance. I'm curious if you think we'll ever reach a point beyond that.
Yeah, I mean, I do basically. So I guess there are like several different things that you can do there. So there's like, does the neural network make like a dumb mistake with real data? And then there's a question of adversarial examples where you try to like take the neural network and look for examples that are going to fool it. So both of these are sort of aspects of sort of like robustness of machine learning models. I guess my interpretation of sort of, so there's this like CLIP model paper result from Alec Radford and OpenAI, which was basically just a multimodal model trained on a very large amount of sort of images and associated captions from the internet. And at least my sort of interpretation of those results was that that model was kind of immediately, in kind of a zero shot sense, much more robust than prior models. And I think my general impression is sort of, well, sample efficiency is not great. You need a lot of data, but these models are kind of like, as you scale them up and give them more data, sort of getting more and more robust. They really sort of understand what the sort of actual ideas that you're getting at when you ask like, what is in this image? And so I guess my interpretation of that is that those kinds of issues are kind of going away. Of course, there are sort of like gotchas associated with that, where you take like a banana and you label it like you write car on the banana and the model says like car. But I mean, I don't really know that that's like the wrong answer. I mean, when you write car on a banana, it does say car there. So I sort of generally think that that's getting better. An interesting reflection of this is I think also these larger, better performing models are actually becoming more interpretable. So if you sort of like do interpretability research on bigger, more successful models, they also like the features that they use tend to become more human interpretable. At least that's the impression that I have. So I think that is kind of going away. There's this like secondary question of adversarial examples where you like literally change the pixels to try to fool the model. And you can do adversarial training against those kinds of attacks. And that also tends to make it harder to sort of attack the model in this way. I think my interpretation of that is sort of that like, maybe people have adversarial examples as well, like optical illusions are a certain kind of adversarial example, but like no one can really differentiate your brain and update the pixels that you're seeing to try to fool you. And so we don't see that. I don't really know. I mean, maybe it's the case that there's sort of a deeper problem here with adversarial examples. My general interpretation is that these things are kind of like improving and kind of going away as you scale up the sort of data set and the power of the model. But I don't know that that's sort of a thing that a point that is kind of universally agreed upon in the community.
And I just have one more question about that. So
Sure.
Even if they kind of will disappear eventually, I don't know if this is kind of something that's discussed more in academia, but do people kind of think about how people are using neural networks right now, but if someone can identify the little bugs in the neural network, they can kind of rewire the entire program.
Yeah, that's definitely, it's definitely a safety concern or like a usability concern. Yeah, that's certainly for sure. I mean, maybe self-driving cars would be the most obvious example where it's like, if a few pixels, yeah.
And is there anything that can be done about that before we like get to a point where those errors aren't a common issue anymore?
Well, I mean, I think the main technique that seems to work is adversarial training, where you go out and find these bugs and then you train the model to not be fooled by them. That seems to work reasonably well. I don't think it works perfectly, but I'm not aware of like a lot of other techniques that really do work. And I think this is a problem. I mean, this is a problem in any situation where there really will be adversaries trying to like fool models. Sorry, I'm not sure if I can hear.
Sorry. Okay. Maybe we'll move on to the next question. If there's follow-ups, you can raise your hand. Jonathan, you can go ahead and ask your question.
Hi, Professor. So this is more back kind of on your physics research side. One thing I kind of related to when you were talking was just that sometimes, you're in the middle of research and you kind of just get the feeling that you both are confused, but then also have no clue kind of how to resolve the confusion. And so just, well, I mean, you can go kind of to a specific example if you'd like, or just kind of on more of a meta level of just kind of what are kind of your go-to strategies when you're just kind of stuck on a research problem.
Yeah. I mean, I've been stuck a lot. And I would say that like, I think research often is kind of this emotional roller coaster for this reason, where like, there's a lot of like, I certainly experience a huge amount of like self-doubt and uncertainty where it's kind of like, well, like, it seems like I did this, like some research projects in the past that were like kind of okay, but like now I'm really stuck and I'm not really sure if I'm ever going to like have a good idea again. So I think that I think it's like, it's just sort of worth emphasizing that it can be pretty painful. I think there's a lot of strategies. I think talking to people about what you're thinking and doing and like what you're trying to accomplish and just having discussions is extremely valuable. Like, I think, especially in physics, like usually when I'm doing physics research, I spend a lot of time like telling my colleagues about like what I'm trying to do. And I think that helps me, even if they don't say anything that insightful, of course, often they do, but even if they don't, like it often helps me to kind of clarify my thinking and like what I'm really trying to accomplish. So I think discussions are probably the number one most obvious thing. I think then trying to think of like toy models and simple examples that sort of still share the feature with like maybe some harder problem you want to solve is always really useful. I think this is also something that I was kind of getting at when I had this slide that I don't know if like what I was getting at was very clear about kind of like abstraction versus concreteness or empiricism or something. Like I think like when I was very young, I had this fantasy that I would just like understand the right abstract idea. And that abstract idea would just be so powerful that it would sort of solve all these problems in an almost magical way. And I think that like that kind of never happens by itself. Like really you have to kind of work through a lot of concrete, explicit examples of something to kind of like get the ideas into your brain in the right format so that you can have the kind of more general insights. At least that's kind of been my experience. I think doing a lot of examples is good. I think like often like trying to figure out exactly what the questions are that you're confused about and like then like reading some stuff in the literature, not necessarily reading in a lot of depth, but just kind of like looking around for other people that have worked on similar questions. Sometimes that'll kind of jog your memory. Sometimes it will like just kind of like trigger something. I think related to that, like my experience with reading the literature, both like papers and books, is that like most things that are out there are really like kind of like not the right thing for you at a particular time, but often you find like the right book or the right paper, and then you're like, oh wow, finally like this person did exactly, like they answered exactly the questions that I had, or they were really thinking about things in exactly the way that like I would think about them, and therefore like you just get like 10 times more out of one particular paper or book than you do out of like lots and lots of other books that sound like they're about the right subject, but they're kind of like not the right thing for you at the time. So I think like often there's some process like that. Often really just forcing yourself to work through an example in a lot of detail is very useful. Like I at least tend to be very kind of like lazy, and I kind of want to like start on something, but then I kind of like I'm like, oh, now I'm gonna have to do this really complicated calculation. I don't want to get involved, or I'm gonna have to write this complicated computer program. I don't want to bother. And so I think often like forcing myself to dive in is fruitful. Even if the thing that I did wasn't directly useful, it just sort of like kind of gets things moving in a way that like kind of thinking about things in a big picture sense doesn't. Then again, there are other styles. I think they're like, I've definitely worked with people who have the opposite style where they kind of like get in, like they go very deep into some rabbit hole and like nothing really comes out of it. It's just like too specific of a problem they're working on. So I think working with someone who has like a different kind of style and orientation from you can just be really valuable, because they'll get unstuck. Like the problems that you get stuck on and they get stuck on will be different. And so together you like kind of like don't get stuck nearly as much. I think that's all I can really say. And like, I don't know, take breaks when you have to, don't get too discouraged, because research is usually really hard.
Thank you.
Yeah, we're running a little bit over time, so I will probably close up very soon. But Professor, is there time for maybe one more question?
Sure, if there's one more question, that's fine.
Yeah, I think there's one in the RSVP that was pretty interesting. So they basically asked, so in like you mentioned in quantum mechanics, for example, one of the sort of revolutionary things about it was that it was backed up by this, speaking theory, it was, the foundations of it were this deep mathematical theory that had been explored pretty thoroughly, like this notion that these physical objects were like abstract vectors in a Hilbert space with this specific mathematical structure. It has like a dual space and certain definitions for like well-defined operations in it. So like it appears that like by setting up an abstract theory for the field of describing quantum mechanics, that gave you access to a lot of really interesting, mathematical machinery. I guess I'd ask, in the field of machine learning today, I surely there must be people kind of trying to make headway to nail down like certain parts of the abstraction in the field, and we're trying to get access to other work that's been done in either physics or mathematics, like over the last few centuries, maybe in something like related to probability theory. What are those? Are there areas, like, is that true? And like, if so, what are those areas that people are trying to make, trying to like connect like data science, machine learning, and so on to the more well studied, I guess I'd say, mathematical theory?
Yeah, so I mean, definitely sort of things that you mentioned are the traditional core. I mean, I think really machine learning is at its core kind of most closely connected to statistics. And there is a tremendous amount of like pretty deep, sophisticated work in statistics. I think like when I was an undergrad, I mean, I didn't really work on AI much. I think I took like one course on AI at some point. But of course I didn't take any courses at all on like statistics. And I probably would have thought at the time, I mean, I guess there's a general trend, which is that like, I don't know, the older I get, the more I like really understand why things that sound boring are actually kind of like deep and exciting. And there are many, many fields like this. So statistics then is one of them. And I guess like at its core, statistics is sort of about like how much can you really learn from information, from data, from like something that happens in the world? Like to what extent and with what confidence and in what sense can you really precisely like know something because an event occurred or because you got a piece of data? And I think that is key to like learning. It's really fundamentally what learning is also about and what AI is about. So I think statistics is really sort of the fundamental home of machine learning and deep learning and stuff like that. That said, of course, like as a physicist, I'm like very, very excited about newer perspectives that are more kind of like rooted in the way physicists think about things. And I think that like my personal opinion, I mean, is really just that, is that machine learning has a lot to learn from natural science. That the only problem with statistics is that statistics is kind of like a branch of math where like statisticians really are very happy to be able to prove rigorous theorems about things. And in physics and in theoretical physics, we often have no idea how to prove a theorem. We don't even have any idea what our assumptions are and what it is that we would be trying to prove if we were trying to prove something. We're really just encountering something very complex and trying to find simple principles that explain at least some of its features. And I think sort of deep learning with these models with billions and trillions of parameters is in this regime where it's kind of too complicated to prove a theorem about. And I do think that very much the approach of natural scientists, of physicists, and to some extent biologists, others are really well suited. I mean, like, I don't know, like famously, like Gell-Mann, when he made up quarks, he had no idea what a quark was. He didn't even think quarks existed, but he realized that there was some assumption he could make that would explain a lot of the data, even if that assumption was fairly rootless. And so I think a lot of approaches that we would naturally take as physicists, where you make up a toy model, it's not really rigorous, it's not exact, but it does sort of capture a lot of the phenomena you see. I think there's a lot of progress to be made with kind of that approach. So I think, I mean, we already discussed like another example is sort of like this large N approximation, the neural tangent kernel. I think that's an interesting theoretical framework. I think there are many others that will be discovered, but yeah, there are a lot of people working on sort of the intersection of these different approaches.
All right, thank you so much, Professor. Yeah, and apologies for going far too long over time, but thank you again for giving a wonderful talk today, and thank you all in attendance. We're going to wrap up today's talk. Thank you for coming today, for your interest in Chilloquium. I hope to see you all at next week's talk, and if you have any questions, comments, or concerns about Chilloquium, please direct those to myself, Andrew Winnicky, and the email I've dropped in the chat just now. Actually, I saw that Professor Kaplan, I think someone asked if you would be able to provide contact, maybe like an email or something, if anyone has any further questions.
Sure. Yeah, I think my email address is on my website at Johns Hopkins, like it's jareddk@gmail. So. Yeah. Okay. Yeah, but thank you so much to everyone for coming.
We have a really exciting lineup of speakers in the next few weeks. We have Andrew Hook from Princeton talking about quantum information science and quantum computing next week. And we have in later weeks, Emmanuel Bloch, Atachi Momoglu, and Michelle Deveray coming up. So stay tuned for an announcement on that. And once more, many thanks to Professor Kaplan for giving a wonderful talk today. Thank you very much.
Thank you. Bye-bye.
Thank you.